Okay, folks, this will be the first video of a few videos I'm going to devote to section 2.3. This homework assignment is due Sunday night. I put the pre-lectures due Saturday night. Hopefully you looked at those a little bit early. A lot of these are pretty computational, hopefully straightforward. So I didn't really intend to cover this too much during class. I'm getting these videos posted probably a little bit late, Sunday afternoon, Sunday evening, really. If you would like an extension on these or other assignments, feel free to request those. But yeah. So what I want to do, section 2.3 is really just a lot of sort of rules and some theorems, different strategies for evaluating limits algebraically. We can do graphical evaluation of limits also, which is really helpful, but we want to be able to do them algebraically. Okay, so I just made a note here. This is from, some of these are in a table on page 95, so if you like the ebook, I might recommend just browsing these tables, maybe writing them down. Page 95's got a few of them. The first table, table number 1, has 5 different rules. Okay, this actually right here is rule number 1 in that list. It's, you could call it the sum rule since I'm adding 2 functions here. And then this bottom one actually, here's number 3 in the list. You could call this the constant multiple rule because I've got a constant multiplied by my function here. This rule is actually listed as number 6. It's on the following page. It's in its own little box on page 96. It's called the power rule because I've got a function raised to a power. Okay, there's some other rules on page 95 in the first table, but I just want to kind of give a basic idea how these work. Then I'll flesh out. Then we'll do one example. Then I'll flesh out the other rules a little bit. Okay. Basically, limits work nicely, meaning that they do what we would like them to do. So what I've got here, when I say limit as x approaches a of, notice in square brackets here, I'm writing f of x plus g of x. So this is assuming I've got 2 different functions. F and g are 2 different functions, but I've created a new function by combining them. Okay, so there's lots of problems in the homework where you're creating new functions by combining them, sometimes composing them. So here, this is one new function. So let's say I have a new function that's defined by adding together these 2 functions. Then essentially you could think about you distribute the limit, right? So the limit as x approaches a of this function is really just the limit as x approaches a of my f function, right? So that limit will give me one number, and then add that to the limit as x approaches a of my second function, g. Okay, so in a sense, it seems like you're sort of distributing the limit. That's kind of the idea, so it works pretty nicely, okay? So rule number 1 in that first table is for a plus sign. Rule number 2 is for a minus sign, right? So we can kind of cover both of those rules together. So if I had changed this to a minus right there, right, if you're subtracting 2 functions, then that just says take the limit of the first one and then subtract the limit of the second one, okay? It also works for multiplication and for division, okay? So you could do that. So I could show the multiplication rule. I think that's, so we had rule number 1 and 2 is addition, subtraction. Rule number 3 jumps down to the constant here. Rules number 4 and 5 are multiplication and division. So that shows the whole table. I could show multiplication here by just putting a dot, and then what I would do is take the first limit, and you could use a dot to represent multiplication, or kind of wrap it in parentheses like that, right, to emphasize that you're multiplying these 2 limits, something like that, okay? And it's true for a quotient, all right? It's true for division. Let me set that up. If I wanted to show the division rule, if I've got this, the limit of one function over another function, then it's just essentially going to be the ratio or the quotient of those 2 limits. So our answer could be that limit divided by this limit. And again, just these limits are just numbers essentially. If limits exist, they could be an infinity or something like that, but usually they're just pretty much whole numbers, or I shouldn't say whole numbers, but some kind of fixed quantity, right? So you can just take the ratio of this quantity. You'll see a little comma in the book, provided this limit does not equal 0, right? I could say provided, let me write that out, that limit as x approaches a of g of x does not equal 0. All right, if it did, then you can't divide by 0, so this overall quotient would not exist. All right, so I'm going to go back to the sum rule because I'm going to use that for my example. But that's the idea. So for those 4 operations, addition, subtraction, multiplication, division, the limit works exactly how we want it to. All right, let me just fill this back real quick. So it looks like nice and neat. That's my sum, and I've got this limit as x approaches a of f of x plus this limit as x approaches a of g of x. Okay, so this top rule, we just explained all 4 rules right there. The 5th one in that table is the constant multiplier rule. So let me just bring that down. And what that says is if I'm going to let x approach the a value for this function, but then those function values are being multiplied by some constant, then what I could do is evaluate the limit, right? Take that limit, again, that limit's just some number, and then multiply that number by my constant. Okay, so kind of pull the constant out in front of the limit. That's a helpful one. You'll see that a lot in Calc 2 when you do integrals, what you do in Calc 2, but it's a helpful one. Okay, so those rules cover what we've got on the first page, or page 95, and then the next rule, I didn't really leave myself so much space. Get rid of this constant multiplier rule. And this one says if I want to take the limit of a function that's being raised to an exponent, then what I could do is take the limit of the function value first without the exponent. That limit's a number, and then take that number and raise it to my exponent, to whatever exponent n this is. All right. So what you'll notice is a lot of these things on the right-hand side of the equal sign, what we're doing is we're taking sort of complicated functions or combinations of functions, sort of complicated pieces, taking the limit of them. And what we end up with is really just looking at just the limit of sort of the original function, just the most basic function. And then we can either add them together or apply exponents or multiply by a constant. And so forth. Okay, so I think a lot of folks probably want to they do these rules without really realizing that they are sort of allowed to use these rules, and that all these rules are classified and labeled, they have titles and stuff like that. But yeah, we just want to be comfortable with them. So let's do an example. I will do an example. I'll combine the 3 original rules that I had on the board. So the sum rule, a constant multiple rule, and a power rule, let's say. So I'll tie all those 3 together. And what I'm going to be doing is an example of what's called direct substitution, okay? Direct substitution, I will make my next short lecture video about. Basically says if you've got a function that you feel like is continuous, and so that's a little bit loose because the definition of continuity is coming up in the future. But specifically, if you've got a function that's a polynomial or a rational function, then as long as your function is defined, you can just plug the value into your limit and essentially just evaluate the function at that spot. If you think the function has something weird going on, like a piecewise function that might have a hole, or something where the function is not defined at a certain value, then the limit might not be so straightforward. So plugging in might cause some kind of issue. But if you can plug it in, and piecewise functions are kind of an exception because they might be defined specifically for one point. But if you've got a nice smooth function like a polynomial, just plug in the answer. So let's say I've got something like this. Let's say I've got a function f of x. Let's say I've got 5x squared plus 3x minus, let's say 5x cubed, up these exponents a little bit, plus 3x squared, and let's say minus 7x. Okay, that's a polynomial. So a polynomial is either a sum or a difference or a combination of those who are adding and subtracting terms. We do not have any x's in the denominator, and we don't have any fraction powers or negative powers. That's the rule. So we want some whole number powers, so quadratics, cubics, things that you're used to. So these functions are nicely defined. Their domains are all real numbers because we're not dividing, we're square rooting, we don't have strange things that might prohibit numbers. So let's say I wanted to evaluate limit as x approaches, let's just say -2 of this function f. Okay. So one way of writing it is like that. I can just write f of x right there because that's the name of the function. Or this means the same thing. I could write x approaches -2, and I could fill in all the terms of the function. 5x cubed plus 3x squared minus 7x. All right. So if you were to, I think there are probably some homework problems where they have you sort of break up all those limit properties, and you'd have to keep rewriting limit and sort of split all these things up. It would become real sort of tedious. Let me kind of show first the calculation that I'm going to do. Then I'll kind of show it using all that limit notation if I wanted to. And let's see what's going on. So direct substitution, I like emphasizing when I'm going to do that, because at this point I'm taking the limit. The limit as x approaches -2 of this thing. What is that equal to? That's going to be equal to plugging -2 in for that, right? So I'm going to get 5 times -2 cubed plus 3 times -2 squared minus 7 times -2. Okay, so all I'm really doing is just evaluating this expression right here when x is negative 2. And so you might say, well, why is that a limit? Why isn't that just f of negative 2, right? And it is. It's actually the function value, and that's also going to be the limit. And again, why is that? Well, this is just some nice smooth function, right? A nice cubic function is nice and smooth. It doesn't have any weird behavior like a hole, or the function seems like it's going somewhere and then it actually lives up here, right? It's just a nice and smooth thing. So if the function exists at a point, right, or let's say you've got a cubic that looks something like this, right? If a function exists right there, if the point exists there, then as you approach that x value from the left, or you approach the x value from the right, you're approaching that spot, right? No funny business. So that's why we're doing what we call direct substitution. We're just plugging the number in to the function. We're not going to do a lot of paperwork in this class, but we will do some. I always ask my students when I do collect paperwork to indicate with a DS, these letters DS, and point to the equal sign when you're doing the direct substitution, so when that step takes place. And the reason why I like to see that is because that's where we drop the limit notation, okay? In other words, this limit as x approaches negative 2, we're sort of telling the reader we're about to do a process. We're about to let x go to negative 2. And so what x? This x, right? So the x is still present in the expression right there because we're about to take x and let it become negative 2. That's what this says. Once we've done that, once we actually let x become negative 2, right, we plugged it in where we saw the x, that means we took the limit. We did the process. So we don't have to set the stage that we're going to take that limit anymore. We already did, right? That's the point. A lot of folks sometimes when they're first learning this, they'll keep writing limit, and we really don't want to. So that's why I emphasize this little ds as sort of a device that realize after you write your ds, after you do your direct substitution, you've done the limit, and so we don't need to write limit anymore. Okay, let's finish this evaluation, then discuss how we're actually using all those rules. Although this is the way I would just show the work, probably not really show all the rules in action. Okay, negative 2, I have to raise this negative 2 to the exponent first before multiplying by that 5, right? That's our order of operations, that phrase or that word. PEMDAS, right? We're familiar with that. PEMDAS, however you want to say that. So negative 2 cubed is negative 8. Negative 8 times 5 is going to give me negative 40. Plus. Now I've got the same idea. I've got to square this negative 2 first, then multiply by the 3. Negative 2 squared is 4 times 3 gives me 12. And finally, negative 2 times 7 is a negative 14. Then I'm subtracting that quantity. So subtracting negative 14 gives me plus 14. And if I could do mental math, that's 26, 40. So I believe negative 14, I want to say, is my answer. All right. That would be my limit. In other words, if you graph this function, really what that's saying, because this is a nice, smooth, continuous function, the point, negative 2, negative 14, should be a point on the curve, right? So that's the function value. So it's also true to say this. So kind of two different statements. F of negative 2 would be equal to negative 14 in this case, because the function's nice and smooth and continuous. But also it's true that the limit as x approaches 2 of that value is also equal to negative 14. Cool, and I hope I added that up right, otherwise I'll be embarrassed, but that seems accurate. Okay, and just on that note, one thing, I'll make mistakes here and there, so call me out on it or be polite and say, hey, I think you made an error if I happen to record it and don't catch it. But one thing I'm less concerned with actually is if you guys add that up right at the end, right? The final answer, it's important, but what I want to see is that we understand sort of the process of how we're doing it, right? And if we make little arithmetic mistakes along the way, we'll try to improve those, but that's not the goal. Okay, let me keep this video short. Let me finish up the idea of the limit properties, the limit rules, the laws, you could argue, that we wrote off the bat. So when I did this, I plugged this in for each value. What we're sort of actually doing right there is, I could say this, right? So let's see what we've got in this. First of all, I've got the sum and the minus. So I'm going to split those up into 3 different limits, right? Limit, limit, limit. So sort of, again, distribute the limit to each of those terms. I want to pull the constants out, and then I want to have the exponents sort of removed as well. Okay, so this first term, the limit as x approaches negative 2 of that term, 5x cubed, I could write as 5 times the limit of just the function x, right? So that's my function f right there, or shouldn't say that. That's not my function f, but that's the piece right there. That's the function as x approaches negative 2, right? And then I'm taking that limit and then cubing that, right? That's the idea. So if I wanted to sort of simplify, you could argue simplify, but it also looks kind of ugly. I've got that going on. The next term would be, I could take, so simply what I'm doing is I want to take the limit as x approaches negative 2 of just x. That's kind of the idea right there. Breaking out that most sort of fundamental function within there. Well, then that x is being squared, so let's square the limit. And then it's also being multiplied by 3, so let's multiply the result of squaring that limit by 3, and so forth. And then the last one would be minus 7 times the limit as x approaches negative 2 of x. All right. And so now you notice the limit statement is as simple as it gets. Let x go to negative 2. And then you're just plugging it in, right? Because your function right there is just x. Let x go to negative 2. Okay, let x go to negative 2. And you do that all around, and what you end up with, if you did the next step, would be what I erased before, right? Kind of the short, intuitive way of doing it. So that's the idea. So don't stress. I don't want to see you guys write this kind of stuff out on paper because it's tedious, waste of paper, waste of time. But just sort of understand that there is a method to this madness that you're sort of doing when you take some shortcuts. Okay, and expect perhaps to see some things like this on your homework. All right, let me end that. Then I'm going to sort of backtrack into direct substitution and then discuss what we call the replacement theorem. All right.